Welcome back. This is lesson 19.1. This week we'll be looking at how to compare algorithms and choose the right algorithm for a particular task. This lesson will be looking in general at how we compare the efficiency and speed of algorithms and how we count the number of operations required by an algorithm. We'll use this method to compare the two search algorithms which we learned about last week, and then we'll see what factors we need to take into account when we're choosing the right algorithm for a job. We typically need to write software to do tasks for us. An algorithm sets out the steps that take us from the inputs to the outputs of a program. Often there's more than one algorithm that we can choose, and last week we looked at how searching can be done by either a linear or a binary search. When we're choosing the right algorithm for our software, one thing that we often do is think about the number of actions that is required, or we say the number of operations that the computer has to carry out, and then we choose the one that is least work for the computer. Why do we count operations rather than just, for example, talk about how fast in seconds it would take to run an algorithm and just pick the one that takes fewer seconds? The reason is that the actual time that an algorithm will take depends on all kinds of other factors, including, for example, how fast your computer equipment is. We want to choose the right algorithm regardless of what computer will be used to run it. We have to think about the number of items that we want the computer to process. So we could run a search algorithm with a very small data set or with a very large data set. The amount of time it takes will vary according to how many items we need to look through. And finally, the speed at which an algorithm completes a task will depend on how quickly the algorithm finds the result in the data set. So let's think about the linear search. When we're searching through a list of data items, if we find the item very early in the data set, the search will stop and the algorithm will be completed quite quickly. But if the item isn't in the data set, then we have to look through the entire set to be sure that it's not there. So for this reason, because the time can vary such a lot, programmers typically think of the worst case. That is, what if it takes a long time to find the right result? And then they compare the worst case for the different algorithms that they've got. Let's look at this in a bit more detail now. When we're counting operations, what do we mean by operations? Well, it literally means any process or action that the computer carries out. But we tend to use it quite loosely because computers are so fast. The difference between a block of 4 lines of code and a block of 3 or 10 lines of code doesn't make a huge amount of difference. What slows the computer down is when a block of code has to be repeated over and over again. So typically when we're counting operations, we tend to ignore a lot of the detail and we just think about how many repetitions there are, how many times a loop has to repeat in order to complete the task. And the number of repetitions is typically related to the size of the data structure that we're processing. So in this example, there are 16 values in this data structure. Because we always want to compare algorithms across all sizes of data structure, we use the conventional letter N to stand for the number of items that we want to process. And we think about the number of repetitions as a function of n. So let's think about the linear search algorithm. Remember, we're talking about the worst case scenario. How many loops would it take to search through this list, and how does this relate to the value n? So make sure you know that. If you need to stop and think, pause the lesson and I'll explain on the next slide. So the number of operations is n. To search a list of 10, you'd repeat 10 times. To search a list of 1,000,000, you'd repeat 1,000,000 times. So it's pretty obvious that the number of loops that are required in the linear search is directly the same as the number of items that you need to search through. But this isn't the case with the binary search. Remember, with the binary search, we split the list in half and take one of the halves and then split that in half again, and we keep splitting and selecting one of the halves until we're down to a list of 1. At that point, we've either found the item or it's not in the list at all. How do the number of repetitions of this algorithm relate to the size of n? How often do we need to split a list of 16 in half and half again until it's down to a list of 1? Have a little think about this. It's an interesting maths problem. Pause the video if you want to have a little go at it, and on the next slide I'll give you the answer. If we split the list in half and half again, it goes like this. It takes 4 operations to split a list of 16 down to 1. Now let's think about it the other way. What if we took the number 1 and doubled it? How many operations does it take to get to 16? The answer is again 4. We're talking about the same process in both directions. So splitting a list of 16 takes 4 operations because 16 can be divided in half 4 times. Or to put it another way, 16 is 2 to the power 4. This tells us the number of operations required as a function of n. The name for this value is log n, log 2n strictly. So 2 to the power 4 is 16, so the log of 16 is 4. And looking down that list of numbers, 2 to the power 7 is 128, so the log of 128 is 7. So the number of operations required as a function of n is log n in the case of the binary search. To summarise, a linear search takes n operations because the computer must look through every item in the list. A binary search takes log n operations. In cases where the list is quite small, the difference between n and log n is not that great. But when n is a large number, like 1,000 or 1,000,000, then the difference between operations is massive. Binary search is much, much faster than a linear search when we're working with large data sets. So we can use this information when we want to choose the right search algorithm for our program. The binary search is a clear winner on speed because the number of operations is log n, a much smaller number than n. So the binary search is faster and the linear search is slower. However, that's not the end of the story, of course, because a linear search can be used on any list, whereas binary searches can only be used on a sorted list. So when you're making a decision about which algorithm to use, you have to be aware of the number of operations required by the algorithm, but you must also be aware of any other factors that are important. And that way you can choose the right algorithm for any particular job that you need to do. So to recap, you should know what an operation is, and we normally simplify it to the number of repetitions. You should know that n is the number of items in a data set, and we express the number of operations as a function of n. You should know the two search algorithms and the number of operations that each one requires, and you should be able to use this information to enable you to compare the algorithms and choose the right one for a particular task. This table shows the number of operations required for a linear or binary search for various sizes of data set, 10 through to 100. The binary search column I've shown literally log of n. Obviously we'd need to round that up to the next whole integer because you can't have a fraction of an operation. So enter that information, let's say into a spreadsheet, round the binary search values up and plot it as a graph, and you'll clearly see how as the size of the data set increases, the difference in operations between the two search algorithms is very marked. Okay, so in the next lesson, we'll look a little bit more at how we can use number of operations to compare algorithms. So bye for now.